recording. Okay, and so I'm going to spotlight myself. Okay. So I want to check, Caitlin, that you can pretty much see this whole area board here.
I do.
Okay, cool. All right, so we're going to look at today, continuing where I started last time. Implicit, and then we'll work our way to explicit solutions for linear ODEs to set the stage for what we'll deal with later with systems of ODEs. So there's a few things from last week that I need to make sure are fresh in your mind. So we're working with the scale ODE minus mu f plus mu y prime is equal to 0, where mu is the as of yet unknown integrating factor, although it was figured out at the end of last time. An implicit solution, capital F of t, y is 0, and therefore, by differentiating that with respect to t, we get ft plus fy y prime is equal to 0. And by matching this, we get dft is minus mu f, and df dy is equal to mu. So the idea is once you have mu, then you can use these two equations to solve for a capital F by integration. Now, I actually worked this out first class, well, to a point, just to show a procedure. I thought, oh, okay, you could integrate both sides of this with respect to y. And this would specify most of capital F, but not everything. Then I would take the result and differentiate it with respect to t and set it equal to this. And that would complete the definition of capital F. Yeah, so you have to use both equations in tandem to find capital F. Now, in what I just described, I said, okay, I'll integrate this one first and then use this to finish it off. But you don't have to. It just depends on the problem, which, like, you could integrate either one of these equations first. You pick one, and then use the other one to help you finish the job. Which one? It just depends on which is easier, because for a specific problem, you'll have a specific little f, you'll have a specific mu. If you go, okay, I'm integrating this with respect to t, or I'm integrating this with respect to y, you just work out whichever integral is easier and go from there. So, all right. Now, to return to where we left off last time, for the linear ODE, y prime is f of ty, where little f of ty is specified to have this form, coefficient times y plus number function q of t. All right. Now, last time, the integrating factor was actually worked out. and it was a function mu of only t, and it was given to be e to the integral of minus p of t dt. All right. So now that we have that, we can make progress towards writing down a solution formula for the original ODE. This is actually my goal for today. I don't plan very much each day, so try to do some digestible chunks. So now we can try to find out, and that will give us, in some form, our solution. So we have a choice now. We can either integrate the one on the surface seems easier. So we have e to the minus, I'll fill in what u is. Okay, and then we integrate that with respect to y. Or we integrate minus that times f, which I fill in here, with respect to t. All right. At least we integrate as much as we can, even with certain things not specified, but we can still arrive at a general solution formula, which is really what we're after. Because this is really what the semester is about, deriving solution formulas for as many cases as we can. Okay. Now, and it's iterated with respect to y, with respect to t, because of which derivatives we have on the left sides of these equations. Because we're trying to solve for capital F. Okay. So, what integral would be the easiest of the two?
It looks like the first one would be, but
yeah, and it turns out it really is. The main reason being that your integrand is a function of only t. We're integrating with respect to y.
Mm-hmm.
So this is the one we'll do. So if you're integrating any function of t, no matter how complicated it may appear, any function of t with respect to y, what's the integral?
Is you believe the t part is like what it is,
Mm-hmm.
and attach the y to it.
Yes.
Yeah.
So it's going to be this times y. Okay. But remember from your Cal 2 class, when you first one to integrate, there's something you always had to do, or your teacher would probably take off points.
Plus a constant, or plus a function now.
Now it's a function.
Yeah.
Yeah. So you can think of it as playing a role of a plus c. And what would that be? It has to be a function that does not depend on y. So any function of t, I'll call it g of t,
Okay.
or capital G of t. That's unknown. Okay, because that way, if I take a derivative of this with respect to y, that would go away. And then the y would become 1. And then you'd have your integrand. Okay, so that's the general solution of that. Okay, so this is capital F of ty, almost completely specified. We just have to try to figure out the rest of this. So to get this far, we made use of this equation. Now we're going to use this one to finish it off. Okay. So now I have to take this and take a derivative with respect to t and set it equal to that. Okay. So let me take a picture of this. So what I've been doing, like I did this after last class. This everything was written on the board, but I took pictures. So then I just typed up notes after that. I'm not sure how quickly I can do that each time. And on Thursday, I was able to do it fairly quickly, but it's difficult to guarantee. Well, it helped that I only had 3 pictures.
Yeah.
Yeah, so the notes are not very long. Okay. Questions up to this point? Or are we missing more? Okay, Caitlin?
I'm good so far. Thank you.
Okay. Okay. So now we use the other equation, df dt equal to minus qf. So we have the derivative with respect, partial with respect to t of the capital F we had so far. That's e to the minus integral of p dt times y plus this is equal to minus, and I got to fill in what u is and f. Try to take advantage of any possible opportunities to simplify things. Okay.
Sorry, I'm trying to, over there after your implication error, is that supposed to be?
Partial derivative with
It's a
respect to
partial
t.
derivative, okay, I'm just making sure.
Yeah, since it's a function of t and y.
Right. Okay, thank you.
Okay. Now, so I take a derivative of this mass with respect to t. Well, the y will just stick around. It's like a constant now. The exponential, we're going to have itself times the derivative of the exponent. But the derivative, but the exponent is an integral. So the integral of a derivative, well, if cancellation here, we'll have minus p of t. Okay. So that is a derivative of this part. And then plus u prime of t. Okay. All right. Now I'm going to distribute the rest, and I'm going to have minus p of t exponential times y, and then I have minus e to the minus p integral p of t dt times q of t. Okay. All right, so now the whole equation is written out for g of t. So what can we simplify?
There is an e negative pt two of the terms on the right side. Maybe pull that out.
There's something else we could do to really cut things down.
Oh, you have two of the same things
Yes.
on each side. So you
We
can
have
use
this
those.
term and this term are identical. So gone, gone. Okay, that was nice. When you have our integrating factor, those are kind of things that happen when you make use of it. So now the equation reduces to g prime of t is equal to minus e minus integral dt dt q of t. And so now we can solve for capital G by integrating. Now we can't really do anything. All we can do is slap an integral sign in front of it.
Right.
So the capital G of t is minus integral of e to, I'll just write it as mu of t, q of t. Right. And there's no need for plus c because it's still an integral, an unevaluated indefinite integral.
Where mu is the integrating factor, right?
Yes. Yeah, just to write less. Okay. So now capital F of ty is completely specified. Capital F of ty is equal to, well, again, mu of t y plus or minus integral of mu of t q of t dt. So now we set that equal to 0. So this equation implicitly defines the solution y.
Implicit solution for y.
Implicit, yeah, of y prime is f of ty when f is of this form for linear PDE. Now, the thing about implicit solutions is what we really like are explicit solutions.
Right.
Y equals something.
Mm-hmm.
Can't always get that, but in this case we can. So our explicit solution. So if we take the implicit solution, this equation, and solve it for y, so now write as y of t. From this, what would it be equal to?
Okay. Wait, for y of t, you just solve for the y?
Yeah.
Yeah, so you could take the, well, I don't know if that makes it explicit or not, or you move the integral over,
Yep.
and then you divide by mu?
Yes.
Yeah, okay.
Yeah, that's all it is. So yeah, so it's 1 over mu of t integral of mu of t q of t dt. So this is our first explicit solution formula for ODE y prime is py plus q. So to make clear, It's for this, the ODEs that fit this form. That's the solution.
Okay, so it's the explicit solution for ODEs of this form.
Yes.
Okay. Okay.
Alrighty. Oh. Okay. Now, and the nice thing is, mu, we already know, in formula for mu, it's exponential. Because it's an exponential, it's never zero.
Right.
So dividing by mu is not going to cause a problem.
Okay.
Okay. Now, what we haven't really talked about, though, is what about initial condition? If you were given this ODE, and now you have a self-solution formula, but now you're supposed to solve an initial value problem. So if you have like y of 0 is equal to some value, like y naught, then how would you take it into account? What you could do is you go ahead and evaluate the integral, which would give a plus c, and then you figure out what the plus c is supposed to be so that the initial condition is satisfied. And in typical classes on these kind of ODEs, I don't know if they ever really state this formula. I mean, I certainly do, but we might describe it more as a procedure. Like, I'll actually have to check the last ODE text that I used, because they change books now and then. That you, like, okay, here's the integrating factor, and now you integrate this, and so forth. But I like to have solution formulas that are as concise as possible. One common mistake that students make with a formula like this, even if they remember this, is when they do the integral, they might forget the plus c. And the thing is, this 1 over mu is going to multiply the plus c. So we have to think about that. But when I was first teaching about this, I was thinking, you know, okay, we have a solution formula, that's all fine and dandy. It's not much to remember here. But it would be nice to have a solution formula that already takes the initial condition into account. So is there a version, is there a way we can go about doing that so that once we get to this point, we have an explicit formula for y of t that that the initial condition, like about the actual value y naught, is already baked in somehow. So that way you're not having to do any extra algebra just to make it satisfy the initial data. Like I don't have to worry about finding some plus c or anything like that. So that would be the ideal situation. So how would I do that? Well, I could basically go through a similar procedure. It's just that I would be using like definite integrals instead of indefinite integrals. So that's how I would have to take that into account. Okay, so as far as how that would go, okay, how much time do I have? Okay, 13 minutes. Keeping in mind that I know what at time 0, like what the solution is supposed to be equal to. Okay. So, and simply something that's consistent with this is a slight change. Okay. Here's the funny part. I know what I'm supposed to get in the end. I use the solution formula all the time. And I know that sometime years ago, like over 10 years ago. I worked out how to get it, but I don't have any of that in my mind right now. So this is going to be all impromptu.
All right.
But knowing what I'm supposed to get in the end, hopefully will help. Okay, so so first thing I'll do is I'm going to define my integrating factor, the exponential of minus, and I'll make that a definite integral. So integral from 0 to t of p of s ds. And the reason for that is, okay, notice I've changed letters inside the integral. I can't say p of t dt anymore because t is a limit.
Right.
So I just choose s. Okay. So what that means is, what basically means that mu of 0 is equal to 1. Because I get e to the 0. Okay. Now, when I carry out the integrals needed to get my capital F, what I did before was I integrated this with respect to y, mu of t dy, and but now I want to change this. So my limits of it, I want to make it a definite integral also. So I'm going to have my limits y naught of the initial value up to y. But now I have to change letters inside. So that's dz. Okay. So that's just going to be mu of t times the difference in limits, y minus y naught. Okay. Okay. All right. Now what I need to do is take the derivative of that with respect to t. All right. So I take the derivative of this with respect to t. That's going to be minus p of t mu of t times, yes, that's right. Times y minus y naught is equal to minus mu times f. So okay.
So we integrated with respect. No.
Differentiated. So
Differentiated with respect to t.
yeah, so this is partial of f with respect to t, which must be equal to minus mu f. All right. Now, as before, certain terms canceled. So I Okay, like minus p times mu times y. Cancel, just like before. So now I have p of t, mu of t, y naught is equal to minus mu of t, something wrong here. Okay, minus mu of t, oh, you know what? Okay. I forgot to add this on. Right, the unknown g of t. So I have g prime of t here. Okay. Whoops. All right, and which I had before. Okay. All right. So, okay. Now, once I simplify everything that I can, so I guess we're doing these things impromptu, I have g prime of t plus p of t, u of t, y naught is equal to minus mu times q, which we had before. Okay. So now,
You said there were some cancellations that took place, we just didn't fully work out.
yes.
Okay.
So, okay. So g prime of t is equal to minus mu of t times p of t y naught plus q of t. Okay. All right. So now we integrate this with respect to t. What I'm going to do is I'm going to make this a definite integral also. G of t is the integral from 0 to t of minus mu of s, p of s, y naught, ds, plus 0 to t of minus mu of s, q of s, ds. Okay. Oh, dang, running out of time, but I think it's all going to work out the way I want it. Okay. I deliberately broke it up into two separate integrals because this one's actually doable. Like, I can't do anything with that. That's just going to be left as an integral. Okay. Because, recall, mu prime is equal to minus p times mu. So the integral of minus p mu is just mu.
Okay.
So I'm undoing that. So g of t is equal to mu of t minus mu of 0 times y naught. Because it's a definite integral. Plus all this. Unchanged. Okay. All right. Now, so now I have g of t that I can add to this, and that should give me my implicit solution. But what I want to make sure of is if I set t equal to 0, that what I'm left with is supposed to be y naught. And yes. Okay. Because notice, if I plug in t equals 0, that's 0, that's 0.
Right.
If I plug in t equals 0 over here, u of 0 is 1.
Right.
And then I have y minus y naught. And that's exactly what I want. Okay, so wait, I need to take a picture of this. Shoot, I'm going to run probably slightly out of time, but okay. So now I can write down the implicit solution. Are there any questions about what happened here?
I'm gonna have to take time to dissect it a little
Okay,
bit later.
well, I'll be writing all this up later anyway.
Yeah.
Okay, so now I can write down all of capital F T Y, which is what I had here before, plus that. So now let's write all that down. Okay, u y minus y naught. Okay. So the implicit solution capital F T Y equals mu of t y minus y naught plus mu t minus mu of 0 y naught plus integral 0 to t of minus u of s q of s ds. Okay, and all of that has to equal 0. Okay. Now, part of what I'm set up for considerable embarrassment is I need to solve this now for y, like before. And like I said, I know what I'm supposed to get. Let's hope it actually plays out that way. So all of this has to move to the other side. So the explicit solution y of t is equal to, well, I'm going to be dividing by mu. That part won't change. And what do we have? We have, well, the last item will be this integral. That doesn't really change either. It's just a definite integral. Okay. And then the other terms that I have are u t y naught. Okay. Minus mu of t y naught. Okay. Oh, actually works out nicely because mu of t y naught, mu of t y naught. Those cancel. Thank God, because like I knew I had too much stuff here. The only thing left is and mu of 0 is 1. So now I just have, why not? Okay, evidently I put left too much room in there. Okay. Now, I want to fill in what mu is as an exponential. So y of t is e to the integral from 0 to t of b of s ds. Because notice it's 1 over mu. Mu has a minus in the exponent, but it's 1 over, so the minus is gone. Times y0 plus this again, 1 over mu, times the integral over here from 0 to t e to the minus 0 to s. And now I need to get another letter inside. P of z dz, q of s ds. Okay. One more thing I can do is I can combine these integrals into one. Because here I have the integral from s to 0, 0 to t. But I can flip the limits and get rid of a minus. So my final form is e to the integral 0 to t p s ds y naught plus integral from 0 to t e to the integral from s to t p of z dz q s ds. So this is what I was really going for in my messy box. And here, it's easy to see that if you plug in t equals 0, the initial condition is satisfied. You plug in t equals 0, that's gone. This whole integral is gone. Only y0 remains, which is what you want. Okay. Whew. Can't believe I still have one more class after this. So this is how far I wanted to get, and I'm just so grateful it all worked out. When I had all these terms here, I was like, something's wrong. But these things cancel that I needed to. Okay. So this is a solution formula that we'll be making very heavy use of later, even with higher order equations that we can rewrite as first order systems. So then we have an analog of this for those kinds of systems, where instead of dealing with ordinary exponentials like we see here, we'll actually have matrix exponentials. Okay, wow, we're on way past time. I mean, I know we're still within a 4 to 5:15 time slot, but I like to end by 5.
Okay.
All right, I'll need time to rest up for 5:60. So, are any questions at this point? Okay, all right. And so look for the notes in Canvas. Well, probably earliest it can be done is tomorrow. Oh, one thing I want to mention. And I might have mentioned this to you earlier, Walker, but when we were meeting. But so this week I had scheduled a visit from my research colleague at NRL, Dr. Pedro Jordan, to come on Thursday and Friday. So my plan was to not have this class. 5:60 will still meet, but since he's up here, I want to make sure to spend as much time possible, so it makes the most of his time. Now he lives in the area pretty hard hit by the storm, so I don't know if he's still coming. I've not heard. Well, okay. To make it easier, because also, you never did hear back from Taylor, did you? Or?
Nothing yet.
Okay. Let's just not have class Thursday. Because now we get to this point, I got to think a little bit about what my next thing I'll cover will be anyway. So not have to wait for some last minute announcement. Yeah.
6:85.
Yeah.
Wednesday.
Yeah.
But still 5:60.
Okay. So I'll see you in the next hour in 5:60. So I'll next see you for this class, and hopefully Taylor too. on Tuesday.
Awesome. I'm gonna just chill in here for
Yeah, I'm gonna chill in my office. All right. Okay.